Oke, kita akan coba ya, mudah-mudahan bisa ya. Tonton bersama beberapa video ya.
Look around you. Everything you see, perceive, and interact with in the real world follows the rules of classical mechanics. This is a study of the motion of bodies in accordance with the general principles first laid down by Sir Isaac Newton. But what about objects that are really, really small? Do they also follow these same laws of classical mechanics? Believe it or not, the answer is no. When things get that small, quantum mechanics takes over, and things start to get extremely weird. Quantum mechanics is the language of tiny particles like photons, the particles that make up light, and the particles inside an atom, such as protons, neutrons, and electrons. To give you a rough idea as to the size of these particles, consider this. The tip of a needle is so large that it could fit billions of electrons. That is how incredibly small electrons truly are. Now that you have a general idea of the size of electrons, let's talk about identities. If someone were to ask, "Who are you?" what would you say? Probably your name, right? Now, let's assume that an anthropomorphic raccoon from another planet asks you the same question. What would you say then? Perhaps, "I am Peter Quill, a human from Earth." In this case, you specified 3 levels of identification. Similarly, in a 3D space, X, Y, and Z coordinates are used to specify an object's exact location, as no 2 objects can have the same X, Y, and Z coordinates. If you consider a 4-dimensional space, with time, t, as an additional dimension, then no 2 particles can have the same 4 coordinates. In the same way, an electron has 4 levels of identification, consisting of 4 quantum numbers. Every electron within an atom has a unique set of quantum numbers. No 2 electrons can share the same combination of 4 quantum numbers. Electrons can be identified using these 4 quantum numbers, which are called the principal quantum number, the orbital angular momentum quantum number, the magnetic quantum number, and the electron spin quantum number. All of these quantum numbers are very important, as they help determine the electron configuration of an atom and the probable location of electrons within that atom. However, for the scope of this video, we're only going to talk about the electron spin quantum number. The definition of spin is the intrinsic value of the angular momentum of a fundamental particle. An electron can either have a positive spin, called spin up, or a downward spin, called spin down. Now, this is where things get bizarre. When we say an electron has a positive spin or a negative spin, it doesn't mean that the electron is actually spinning. Although it does have angular momentum and proper magnetic orientation, it's not exactly spinning. It may actually exist in a state of superposition, when it has both a negative and positive spin. You may find the idea of superposition confusing, because this doesn't seem to go along with our perception of the real world. To help explain this a bit better, here's a famous example for understanding superposition. You might have heard of Schrödinger's cat. This is a famous thought experiment devised by Austrian-Irish physicist Erwin Schrödinger. It goes something like this. Imagine that you put a cat inside an opaque, soundproof box, along with a radioactive substance, a vial of poison, and a Geiger counter. If the radioactive substance decays, then the Geiger counter triggers a setup that releases the poison, thus killing the cat. However, the decay of the substance is a random process, so there's no way to predict when it will happen. And that is why, before opening the box, you can say that the cat is in a superposition of being both alive and dead at the same time. In the same way, when a coin spins on a flat surface, it's in a state of superposition between its 2 faces, heads and tails. Similarly, electrons in their natural state exist as a superposition of both up and down spin. Only when measured do they give a definite value of up or down, which, in technical terms, is referred to as the collapse of the wave function. In quantum mechanics, wave function collapse occurs when a wave function, which was initially in a superposition of a few states, reduces to a single state due to interaction with the external world. When a pair of electrons are generated, interact, or share spatial proximity, their spin states can get entangled, which is what scientists call the quantum entanglement of electrons. Once the electrons are entangled, the two electrons can only have opposite spins. That is, if one is measured to have upspin, the second immediately becomes downspin. Now, we know that the two electrons, unmeasured, do not have a single spin, but a superposition of both up and down spin. If we were to separate the two electrons arbitrarily far, say, we put one in a physics lab on Earth and another in a different lab somewhere in the Andromeda galaxy, and we measure the spin of the electron on Earth, we will immediately know the measurement of the one in the Andromeda galaxy. For example, if we measure the Earth electron to have upspin, we immediately know that the other electron has downspin. This information traveled instantaneously, faster than the speed of light. As one can imagine, this idea greatly bothered famous physicist Albert Einstein. It was such a disturbing realization, in fact, that he called this phenomenon spooky action at a distance. So how can this spooky action at a distance be useful to us? Well, let's start with one of the most common everyday objects, the clock. Having a common synchronized clock is very important in today's world. They keep things in line, like stock markets and GPS systems. Today, we have extremely precise clocks, known as atomic clocks. The quantum logic clock at the U.S. National Institute of Standards and Technology, NIST, in Colorado, will neither lose nor gain 1 second in some 33 billion years. Entangled atomic systems would not be preoccupied with local differences and would instead solely measure the passage of time, effectively bringing them together as a single pendulum. That means adding 100 times more atoms into an entangled clock would make it 100 times more precise. Entangled clocks could even be linked to form a worldwide network that would measure time independent of location, vastly expanding the technology of GPS systems and telecommunication. Then, of course, there's quantum cryptography. As a kid, did you ever make up a secret code language that only you and your best friend could understand? Imagine that, but with the key to cracking the code being randomly polarized photons entangled with each other. That is quantum cryptography. Today, some tech companies use QKD, quantum key distribution, to design ultra-secure networks. In 2007, Switzerland tried out an ID Quantique product to provide a tamper-proof voting system during an election. This system promises to be highly secure because if the photons are entangled, any changes to their quantum states made by intruders would be immediately apparent to anyone monitoring the system. Researchers at Japan's Hokkaido University developed the world's first entanglement-enhanced microscope using a technique known as differential interference contrast microscopy. Using entangled photons greatly increases the amount of information the microscope can gather, as measuring one entangled photon gives information about its partner. How about quantum teleportation? Is it possible? Yes, teleportation is possible in the world of subatomic particles, but it's entirely different from the way teleportation is depicted in movies and popular culture. Quantum teleportation involves the transportation of information rather than the transportation of matter, which is the specific type of teleportation typically focused on in science fiction. Physicists continue to delve into and understand more about the capabilities of quantum entanglement. Once we are able to fully harness this knowledge, it could potentially revolutionize every aspect of our existence. Until then, we will continue to try and make sense of the principles of quantum mechanics because, let's face it, it's a strange branch of science that doesn't seem to make any sense in the real world. Basically, as Nobel laureate Richard Feynman once said, if you think you understand quantum mechanics, you don't understand quantum mechanics. If you like this video, then please leave your comments below and subscribe to our channel for more animated stories on the science in our lives. Also, don't forget to hit the bell icon to never miss an update from us.
I recently gave a talk here at the RI on quantum
Luar
mechanics,
biasa ya,
which
sebentar ya.
I was very pleased to see got a big response.
Kita
However, some
break
people,
sebentar ya.
some viewers of that talk expressed